In the previous video, we derived this differential form of the general balance equation for any extensive property per unit mass, psi hat, using this control volume, the boundary of which is aligned with the axes of the Cartesian coordinate system. When doing this, we took the limit as delta x, delta y, and delta z go to 0. Therefore, this equation describes the transport in an infinitesimally small region of space. Therefore, it isn't necessary for us to describe how, for example, the flux due to diffusion or advection changes over this surface area, or how phi might change within this volume, because it's an infinitesimally small volume. Now let's consider a general control volume of irregular shape and non-infinitesimal dimensions. The integral form of the generalized balance equation for any extensive property psi accounts for the accumulation of psi integrated over the entire volume. This occurs due to the net advective flux across the control volume boundary integrated over the entire surface area of the control volume, the net diffusive flux across the control volume boundary, again integrated over the entire control volume boundary, and the volumetric rate of generation of the property psi integrated over the entire control volume. Each of the flux terms, the advective and diffusive flux, are integrals of a dot product with a vector n. The vector n is a unit normal vector that always points outward from the surface. By taking the dot product with the unit normal vector n, we can account for the fraction of the transport that crosses the system boundary. This is necessary because the direction of the advective flux, or the diffusive flux, may not be perpendicular to the surface. Remember that the dot product of two vectors is a scalar. If the flux is parallel to the unit normal vector, then all of that flux is leaving the control volume, hence the minus sign. If that dot product is anti-parallel to a unit normal vector, then all of that flux is entering. But when two vectors are anti-parallel, meaning they point in opposite directions, their dot product has a negative sign. That's why we need the negative sign in front of these surface integrals. For the dot product of two vectors that are at some non-zero angle to each other, the magnitude of the dot product is less than the product of the magnitudes of the two vectors. And when the two vectors are orthogonal, or meet at 90 degrees, then the dot product goes to 0. That would be the case for a flux that is in a direction parallel to the surface. A flux in the direction parallel to the surface does not cause any psi to cross the surface, and so the dot product goes to 0. This form of the integral balance equation combines both surface integrals and volume integrals. The divergence theorem relates surface and volume integrals, so we can use the divergence theorem to convert these surface integrals to volume integrals. The divergence theorem says that the integral over any bounded surface of a vector field dotted with the unit normal to that surface is equal to the integral over the volume bounded by that surface of the divergence of the vector field. Since we have the dot product of a unit normal vector and a vector field in each of these surface integrals, they can be converted using the divergence theorem to the corresponding volume integrals. Then we can take all of the volume integrals and combine them on the left-hand side of the equal sign. Notice the advective and diffusive flux terms here that were dot products with unit normal vectors are now converted to divergences. This is an equivalent integral form of the balance equation for the extensive property psi over any bounded Eulerian control volume. Now to derive balance equations for quantities of interest, we'll replace psi, the diffusive flux term J, and the volumetric rate of generation phi with the appropriate variables. First, we'll do this for the mass balance. If the transported property per unit volume, rho psi hat, is mass, then rho psi hat is simply equal to rho. There is no diffusive flux of total mass because the advective transport term, by definition, accounts for the bulk flow of mass. So all of the mass flux is in the advective transport term. Also, we know from the conservation of mass that mass is neither generated nor consumed by chemical and biological processes. Therefore, its volumetric rate of production should always be 0. The total mass balance is called the continuity equation. Psi hat is simply mass per mass, so that's just 1. We already said that the diffusive flux of mass is equal to 0 because the movement of mass is described by the advective flux, and the rate of generation of mass is also 0. Making those substitutions into the differential form of the general balance equation, we find a simple relationship for the conservation of mass. The conservation of mass we call the continuity equation. It's very important because it can be used to simplify other transport equations. According to the conservation of mass, d rho dt is always equal to minus the divergence of rho v. So in the generalized transport equation, we can use the continuity equation to simplify these two terms, which will always contain d rho dt and the divergence of rho v. Now we can write a generalized transport equation for any extensive property per unit mass psi hat that does not contain the d rho dt term or the divergence of rho v. We'll use this differential form of the general balance equation for all other extensive quantities. In the next video, we'll derive the Cauchy momentum equation. If you haven't seen it yet, the Cauchy momentum equation will soon make an appearance in CBE 331.